Hi everybody, this is Mr. Yeoman again, and today what we're looking at is bond energy. The last couple days we've been discussing um, energy, specifically in the form of heat, but today what I want to do is take a look at that bond energy that we were discussing. So knowing that every bond that is made requires energy in order to form that bond, it also requires energy to break that bond. So a certain amount of energy would be released in that process. Um, is what we're going to try to figure out is we're going to have some problems that try to determine the amount of energy that is required to break those bonds in the reactants as well as build those bonds in the product. So this should look familiar. Comes straight out of the worksheet that we're working on today in your packet. It says bond energy at the top. And so this just gives energies for individual bonds. So you can see that each bond is between two atoms. Some of these are single, double, or even triple bonds. Um, right beneath there, I have an equation. Now this is written in a little bit of a different way. Instead of writing out the formulas, I have the Lewis structure here, which I think will help identify what the bond energy is for each item. So looking at this first one, we have a hydrogen bond, so we can come right up here, see that it is 436 kilojoules per mole. And so we can actually just write that in there, knowing that that's what we're going to be working with initially. Okay, our second item is a chlorine-chlorine bond. So if we come right over here to 242 kilojoules per mole, we know that we can plug that right in. There's 1 mole of that as well. So this takes care of our reactants, and it tells us how much energy is going to be required in order to break those particular bonds. Well, that allows us to move on to the product side, which has our hydrogen and chlorine. Now, our hydrogen and chlorine are bonded together. Right over here, we have a value of 431 kilojoules, so we plug that into our equation. But this time we have 2 of them, so I just wrote them side by side, and having it added together like that allows us to do some simple arithmetic. Say that on our reactant side we have 678 kilojoules per mole, and on our product side we are releasing 862 kilojoules. Allowing us to plug this into our equation that's on your sheet. So what we want to do is figure out the change in enthalpy for the entire reaction. Now, as we discussed, the change in enthalpy is really just saying how much heat is being increased or decreased. So on that reactant side, what we're trying to say is how much energy is used for breaking those bonds, and we want to subtract the amount of energy formed in making those new bonds. So we can just plug in our energy from our reactants down here below and subtract the amount from our products. And so in this case it gives us a negative number. Now what that negative number is telling us is that there is an excess amount of energy. If you can see here, the amount of energy used for breaking the bonds is less than the energy that is formed from making the new bonds. So that's why that negative number is telling us that it's an exothermic reaction. So if the delta H, the change in enthalpy, is a positive number, say the reaction is endothermic, it needs to absorb more energy in order to form these products. If the delta H is negative, then the reaction is exothermic, that is giving off excess energy. Okay, so I want to take a look at something that's a little bit more complicated. Same concept. But now, looking at these Lewis structures, we have more bonds. Before we just had single bonds between 2 atoms. Now we have multiple atoms that are bonding in multiple places. So it's going to look a little bit different. So we have 4 carbon-hydrogen bonds in this one, and 1 carbon-carbon double bond. We have 1 fluorine-fluorine bond, and then over here we have 1, 2, 3, 4 carbon-hydrogen bonds. We have 2 carbon-fluorine bonds and 1 carbon-carbon bond. So the process is the same, it just looks a little bit more complicated. So for example, we're going to take a look at our carbon-hydrogen bonds. So again, we know that that 413 kilojoules per mole is fine, except, as we discussed before, there are 4 of them. So we need to make sure that we account for all 4 of those. Essentially, that's an extra mole that we are looking at. Okay, but now we also have the 2 fluorine atoms that are bonded to one another with 155 kilojoules per mole. I'm sorry, the carbon-carbon bond has 614 kilojoules per mole. Now we go to the fluorine bonds with 155 kilojoules per mole. Now, I'm running out of room here, so I'm going to go down to the next line and start my next one. But again, I have 4 carbon-hydrogen bonds, so I need to take those times 4 again. This time I have 2 fluorine carbon bonds, so I'm going to take this one times 2. But then for the last one I have a single carbon-carbon bond. So that is 348 kilojoules per mole. Again, going back up to the table. And I'm just pulling all this information straight out of there. Okay. Now, if I simplify this and I do a little bit of arithmetic, I end up with 2,421 kilojoules per mole and 2,382 kilojoules per mole. Now, if I use the exact same equation, all I'm looking at are my reactants and my products. I'm trying to figure out, I have 2,421 kilojoules per mole, and then I'm going to subtract my 2,382 kilojoules per mole. Okay, which gives me 39 kilojoules per mole, telling me this is an endothermic reaction. I'm going to need more energy in order to form this reaction. Okay, so most of the time, your equations are going to be given to you something like this. Now, this is going to be a little bit different because what I'm going to ask you to do, or at least in this situation, what you're going to have to do is determine what that Lewis structure would look like. So I've gone ahead and I've done that for you. I drew this out using Marvin's sketch and made these diagrams ready to go for you. But we can do the exact same thing. So we have a hydrogen-hydrogen bond with 436 kilojoules per mole. We have a carbon and an oxygen, which is double bonded to one another. And so, again, we can go up here and we're going to say, all right, so that's 799 kilojoules per mole. But there is one set here and there's another set here. So we're going to take that times 2. And then on the other side of the reaction, we have a water molecule with 2 oxygen-hydrogen bonds. So an oxygen-hydrogen bond here, an oxygen-hydrogen bond here. So I'm going to take that times 2. And then last, for my carbon monoxide, I have a triple bond. So I need to add that in. Now, as you can tell, the triple bond is much more energetic than all the other bonds. So to form this, it's going to look a little bit different. So we have 2,034 kilojoules. And we have 1,998 kilojoules. So this leaves us with the same equation that we've been working with, where we are trying to determine the change in enthalpy of the entire reaction. So we're going to take the amount of energy that is required to release, to break those bonds, and we're going to subtract the amount of energy that is given off by forming those bonds. So we're left with an endothermic reaction that requires 36 kilojoules per mole because it requires more energy in order to make all this work. So I'm hoping this helps you out. Try out a few of these problems with your friends. And then when I get back tomorrow, hopefully we'll be able to pick up and I can answer any questions that you have. Thank you. Have a great day.